Almost nothing about him survived. No portrait, no diary, no letters to friends describing his day. And yet this man, who left behind almost no trace of his personal existence, created something so powerful that every educated human being, for the next 2,000 years, would know his name. Euclid of Alexandria, the father of geometry, the author of the most successful textbook ever written. But here's what makes his story stranger than you might expect. We're going to reconstruct the life of someone we know almost nothing about. We'll walk through ancient Alexandria when it was the intellectual capital of the world. We'll watch the creation of a book that would outlast empires, and we'll discover why a man who probably never intended to be famous ended up shaping human thought more profoundly than most kings or conquerors ever could. The challenge isn't just that the evidence is thin, it's that what we do have raises more questions than it answers. Why did his masterwork survive when so many others vanished? What was it about this particular mathematician in this particular city that allowed him to capture something eternal? The answers lie not in grand monuments or detailed chronicles, but in fragments, in what got preserved by accident, in the shadow he cast across mathematics itself. Let's start with what we actually know, then we'll fill in the world around those facts until a life emerges from the silence. Alexandria, in 300 BC, wasn't just another Mediterranean port. It was barely 30 years old, and it was already becoming something unprecedented. Alexander the Great had founded it during his conquest of Egypt, placing it strategically where the Nile Delta met the sea. But Alexander died young, and his empire fractured. Egypt fell to one of his generals, Ptolemy, who had bigger ambitions than simply ruling. Ptolemy wanted to build something that would outlast military conquest. He wanted Alexandria to become the center of human knowledge. The timing was extraordinary. Greek culture was at its peak. Philosophy, mathematics, medicine, astronomy, all of these fields were exploding with new ideas, but they were scattered across dozens of city-states and colonies. Ptolemy saw an opportunity. What if you could gather the best minds in one place? What if you could collect all human knowledge under a single roof? So he built the Library of Alexandria, not just a collection of scrolls, but an institution, a research centre. Scholars were given salaries, housing, and freedom to pursue their work. The library sent agents across the known world to acquire texts. Ships arriving at Alexandria's harbour were searched, and any books found were confiscated, copied, and the copies returned to their owners, while the originals stayed in the library. It was systematic, ambitious, and absolutely ruthless in its pursuit of knowledge. This was the world Euclid entered. We don't know exactly when he arrived in Alexandria, or where he came from before that. Some ancient sources suggest he studied in Athens, at Plato's academy, which would make sense. The academy was the premier mathematical institution of the Greek world. Plato himself had supposedly inscribed above its entrance, "Let no one ignorant of geometry enter here." If Euclid did study there, he would have been immersed in a particular way of thinking about mathematics, not just as practical calculation for commerce or engineering, but as a path to understanding reality itself. The Pythagoreans believed that number was the fundamental substance of the universe. Plato argued that mathematical forms were more real than the physical objects we perceive with our senses. A perfect circle drawn in sand will wash away, but the concept of a circle, the definition, the properties, the relationships it holds, that exists in a realm beyond physical destruction. This philosophical framework shaped everything Euclid would later write. But first he needed to navigate the intellectual ecosystem of early Alexandria. Picture the scene. The library complex sprawls along the harbour. Inside, scholars from across the Mediterranean world gather. They speak different dialects of Greek, come from different philosophical schools, and often disagree violently about fundamental questions. The head librarian during Euclid's time was likely Zenodotus of Ephesus, a literary scholar trying to establish definitive texts of Homer's epics. In the same building, physicians were dissecting corpses to understand anatomy, astronomers were measuring the movements of planets, poets were experimenting with new meters, and somewhere in this chaos, mathematicians were arguing about proofs. Here's what made the mathematical community different. A poet could write verses that some loved and others hated, and there was no objective way to settle the dispute. But mathematics promised something else entirely: certainty. If a proof was valid, it was valid everywhere, for everyone, forever. The angle sum of a triangle wasn't a matter of opinion or culture, it was simply true, except there was a problem. Mathematical knowledge had accumulated over centuries. The Babylonians had developed sophisticated techniques for solving practical problems. The Egyptians had their own methods for surveying land and constructing monuments. Greek mathematicians like Pythagoras, Hippocrates of Chios and Eudoxus had made brilliant discoveries. But it was a mess. Results were scattered across different texts. Some proofs were rigorous, others were intuitive arguments that happened to work. Some theorems were stated precisely, others were vague. And worst of all, different mathematical schools used different foundational assumptions. It was like having the parts of a magnificent building scattered across a field, with no blueprint showing how they fit together. Someone needed to organize it, to sort out what was actually proven from what was merely plausible, to establish a clear foundation and build systematically from there, to create a definitive text that would show once and for all what geometry actually knew. This is what Euclid set out to do. Not to discover entirely new mathematics, though he probably contributed some original results, but to organize, systematize, and prove rigorously everything that was known. It sounds like a modest goal. It wasn't. Think about what this required. First, he had to decide what the absolute foundations would be. What basic truths would he take as given, and what would he prove from those foundations? Second, he needed to determine the logical order, which theorems depended on which others, what needed to be proven first to make later proofs possible. Third, he had to develop a consistent style of reasoning that would work throughout the entire system. And fourth, he had to do all of this in a way that was clear enough for students to follow, but rigorous enough to satisfy the most demanding mathematical minds. The result was the Elements, 13 books. Not books in our modern sense, these were scrolls, probably taking up several dozen papyrus rolls when complete. The work opens with definitions, postulates, and common notions. These are the foundations, the bedrock assumptions that everything else builds on. Then it proceeds, step by step, theorem by theorem, through the entirety of geometric knowledge. Book 1 covers basic plane geometry, triangles, parallel lines, the Pythagorean theorem. Book 2 deals with geometric algebra. Books 3 and 4 explore circles and polygons. Book 5 develops the theory of proportion, abstract, difficult, and absolutely crucial for everything that follows. Book 6 applies that theory of proportion to plane figures. Books 7 through 9 cover number theory. Book 10 tackles irrational magnitudes. Books 11 through 13 extend the treatment into 3 dimensions, culminating in the construction of the 5 regular solids. It's a monument of human reasoning. And we need to be clear about what makes it remarkable, because it's not always what people think. Euclid didn't invent most of the mathematics in the Elements. Historians estimate that perhaps only a quarter of the results are original to him. The Pythagorean theorem, that was known for centuries before Euclid was born. The technique for finding the greatest common divisor, probably not Euclid's discovery. The construction of the 5 regular solids, that goes back to the Pythagoreans and was refined by Theaetetus. So why does Euclid get the credit? Because discovery and organization are different achievements, and sometimes the second is actually harder than the first. Consider what he accomplished. He took hundreds of geometric results, some proven rigorously, some not, some contradicting others, some using different foundational assumptions. and he wove them into a single coherent system where every statement follows logically from what came before. He identified exactly what needed to be assumed at the start. He determined the minimum number of postulates required, and he maintained absolute logical rigor for thousands of propositions. This wasn't just teaching, it was architecture of thought. The influence was immediate. Within a generation, the Elements had become the standard geometry text across the Greek-speaking world. Other textbooks were gradually abandoned. Why copy and preserve them when Euclid's treatment was clearer, more complete, and more rigorous? The older texts disappeared. Not because they were burned or banned, but because scribes making copies for new students chose Euclid instead. But we're getting ahead of ourselves. We need to understand what Euclid's daily life actually looked like. What did a mathematician do in Alexandria around 300 BC? The answer is, we mostly don't know. But we can reconstruct the outline. He almost certainly taught. The ancient sources refer to him as a teacher, and there are anecdotes about his students. Teaching in the ancient world meant something different than it does today. There were no classrooms in our sense, no formal curriculum imposed from above. Instead, a teacher would gather students, usually young men from wealthy families who could afford the time for education, and work through texts and problems with them. The relationship was intensely personal. A student didn't just learn mathematics from Euclid, he learned how to think about mathematics, how to approach a problem, how to construct a proof, how to spot a logical gap. These weren't skills you picked up from reading a book. They required direct interaction, question and answer, the teacher watching the student work through a problem and intervening at the exact moment when intervention would be most helpful. There's a famous story about Euclid and one of his students. A young man had just learned the first proposition in geometry and asked, "But what shall I gain by learning these things?" Euclid called his slave and said, "Give him a coin, since he must make gain out of what he learns." The story might be apocryphal. Most of these ancient anecdotes are. But it captures something real about Euclid's attitude. Mathematics wasn't a path to wealth or practical advantage. It was valuable in itself, as a form of knowledge, as a way of understanding truth. If you couldn't see that, you were missing the entire point. And yet, Euclid had to eat. He had to pay rent. The image of the unworldly mathematician living on air and abstraction is romantic but false. Someone was funding this work, and we need to understand who and why. The Ptolemaic dynasty wasn't supporting scholarship out of pure altruism. They were building a brand. Alexandria was a new city in a conquered land ruled by foreigners. The Ptolemies were Macedonian Greeks governing a population that was overwhelmingly Egyptian. They needed legitimacy, and culture was how you bought it. So they poured resources into the museum and the library. They invited the best minds in the Greek world to come work in Alexandria, offering salaries, housing, and access to the greatest collection of texts ever assembled. It was a calculated investment in prestige, and it worked. Within a generation, Alexandria had replaced Athens as the intellectual capital of the Mediterranean. Euclid was part of this project. He wasn't just teaching geometry for its own sake. He was helping establish Alexandria's reputation as the place where knowledge was taken seriously, where rigorous thinking happened, where the traditions of Greek philosophy and mathematics would be preserved and extended. But there's something strange we need to address. For all his fame, we know almost nothing about Euclid's personality. Was he kind, arrogant, patient with slow students, or contemptuous? Did he have a family, friends, interests outside mathematics? The silence is nearly total. The ancient biographers, who preserved colourful details about other scholars, somehow recorded almost nothing about Euclid's character or private life. We have the anecdote about the student and the coin. We have a story about King Ptolemy asking if there was an easier way to learn geometry, and Euclid replying that there is no royal road to geometry. That's essentially it. This absence is telling. It suggests that Euclid's personality wasn't particularly memorable. He wasn't an eccentric like Pythagoras, who founded a religious cult. He wasn't a provocateur like Socrates, who got himself executed. He wasn't a celebrity intellectual like Aristotle, who tutored Alexander the Great. He was apparently a competent, serious teacher who wrote an extraordinarily important book and then faded into obscurity as a person while his work lived on. Actually, that's not quite fair. His work didn't just live on, it dominated. For more than 2,000 years, the Elements would be the geometry textbook, not one of several competing approaches. The approach, the standard against which everything else was measured. Think about what that means. A text written in Alexandria around 300 BC was still being used to teach geometry in Europe in 1900 AD. That's a span of 2,200 years. No other textbook in human history has had anything close to that kind of staying power, not even the Bible, which underwent constant reinterpretation and translation. The Elements remained fundamentally the same text, teaching the same methods, making the same arguments. Why? What made it so durable? Partly it's the rigor. Euclid set a standard for logical proof that no one before him had quite achieved, and no one after him could afford to ignore. If you wanted to teach geometry properly, you had to teach it Euclid's way, with axioms and postulates and step-by-step deductive proofs. Any other approach felt sloppy by comparison, but there's more to it than that. The Elements works because it's pedagogically brilliant. The propositions are arranged in a sequence that builds understanding gradually. Easy results come first, harder ones build on them. The most difficult and beautiful theorems appear near the end. After you've developed all the tools, you need to understand them. This seems obvious now because we've inherited Euclid's approach, but it wasn't obvious in 300 BC. Earlier geometry texts apparently just presented results in whatever order the author felt like. Euclid imposed structure. He understood that mathematics isn't just about individual proofs. It's about seeing how everything fits together into a coherent system. The Elements has 13 books, not chapters, books. In the ancient world, a book was a scroll, and you couldn't fit much on a scroll. So a long work had to be divided into multiple scrolls, each one called a book. Books 1 through 4 cover what we now call plane geometry. Triangles, parallel lines, circles, the construction of regular polygons. This is the material most people encounter in school, and it's where Euclid is at his most familiar. Book 5 is different. It's about proportion and the theory of ratios, and it represents some of the deepest and most sophisticated mathematics in the entire work. The theory here is due to Eudoxus, one of the great mathematicians of the generation before Euclid, and it solved a problem that had troubled the Pythagoreans. How do you deal with irrational quantities, numbers that can't be expressed as ratios of integers? Eudoxus's solution was brilliant, and Euclid preserved it. Books 7 through 9 shift to number theory, what we'd now call arithmetic, but approached geometrically. The Euclidean algorithm for finding the greatest common divisor appears here. So does the proof that there are infinitely many prime numbers, one of the most elegant arguments in all of mathematics. Book 10 is notoriously difficult. It classifies different types of irrational lines, and even in the ancient world, it was considered obscure. Most students probably skipped it. Books 11 through 13 return to geometry, but now in 3 dimensions. Solid geometry, the construction of the 5 regular solids, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron, appears in Book 13, and the text culminates with the proof that these are the only regular solids possible. This structure reveals something important. The Elements isn't just a geometry book. It's a systematic presentation of the mathematical knowledge of its time, organized to show how everything connects. Number theory, geometric proportion, plane figures, solid figures, it's all one unified body of knowledge, built from the same foundations. Now here's where things get interesting. The Elements spread rapidly across the ancient world, but not always in Greek. Within a few generations, it had been translated into Latin for the Roman world. Later, it would be translated into Arabic, and it was through Arabic translations that medieval Europe first encountered Euclid after the fall of Rome. The Greek original was nearly lost. Almost every copy disappeared during the chaos of the early Middle Ages. The text survived because Islamic scholars preserved it, translated it, studied it, and eventually transmitted it back to Christian Europe. This pattern repeats throughout history. Knowledge doesn't flow in one direction, it circulates. The Greeks learned from the Babylonians and Egyptians. The Arabs learned from the Greeks. The Europeans learned from the Arabs. Each culture preserved, refined, and extended what they received. Euclid's elements became a kind of universal inheritance, belonging to no single people, but to everyone who studied it. But we need to be careful here. When we say the elements was used continuously for 2,000 years, we don't mean it was unchanged. Each new generation of scholars added commentaries, alternative proofs, additional propositions. The medieval Arabic mathematicians extended Euclid's work in ways he never imagined. Renaissance European scholars tried to improve on his proofs, or fill in gaps they perceived. The most famous controversy centered on the fifth postulate, the one about parallel lines. It seemed more complicated than the others, and for 2,000 years mathematicians suspected it wasn't really a fundamental assumption, but could be proved from the other postulates. Countless attempts were made. All failed. It turned out the fifth postulate really was independent, and the attempts to prove it eventually led to the discovery of non-Euclidean geometry in the 19th century. But that's a story for later. What matters now is understanding what Euclid accomplished. He took the mathematical knowledge of his time and organized it into a system so clear, so rigorous, so pedagogically effective that it became the foundation for all subsequent work. He set the standard for what a mathematical proof should look like. And he did all of this not through genius discoveries of his own, but through the arguably harder work of synthesis and organization. There's a lesson there about the nature of intellectual achievement. We tend to celebrate the brilliant individual who makes the breakthrough discovery. But sometimes the person who organizes and systematizes existing knowledge does more to advance a field than the original discoverers. Euclid wasn't necessarily a greater mathematician than Eudoxus or Theaetetus, but his contribution was in some ways more valuable because it made their work accessible and usable for everyone who came after. The elements became more than a textbook. It became a model for how to think. For centuries, educated people learned logic by studying Euclid's proofs. The method of starting from axioms and deriving conclusions through rigorous deduction became the template for all rational inquiry. When philosophers wanted to present their ideas with mathematical certainty, they wrote in the style of Euclid. Spinoza's Ethics is structured like a geometry text with axioms, definitions, and propositions. Thomas Hobbes thought political philosophy should proceed geometrically. Even Newton's Principia, which established the laws of motion and gravity, was written in the Euclidean style, with theorems and proofs. This influence extended far beyond mathematics. The idea that you could start with a few simple assumptions and build an entire system of knowledge through logical deduction became one of the defining characteristics of Western thought. It shaped how scientists approached nature, how lawyers constructed arguments, how architects designed buildings. The Euclidean method became a way of seeing the world. But here's what's strange. For all this influence, Euclid himself remained a ghost. His book became immortal while he disappeared. We don't know when he died. We don't know where he's buried. We don't know if he had students who carried on his work directly, or if the elements just spread independently through copying and study. The man vanished while his creation endured. Maybe that's appropriate. Maybe it's even what he would have wanted. The ancient Greeks had a concept called kleos, glory, the fame that survives death. For most people, kleos came through heroic deeds, through achievements in war or politics that would be remembered in song and story. But for a mathematician, kleos could come through something different, through a proof so elegant it couldn't be forgotten, through a method so powerful it would be used forever, through a book that would teach thousands of generations. Euclid achieved that. His Elements outlived empires. It survived the fall of Rome, the rise of Islam, the Renaissance, the scientific revolution. It was still being published in new editions in the 20th century. Even now, when we've moved far beyond Euclidean geometry into strange new mathematical territories he couldn't have imagined, we still teach his methods to children. We still use his approach as the foundation. The geometry you learned in school, if you learned any geometry at all, was Euclidean geometry. The proofs you struggled through, the constructions you made with compass and straight edge, the theorems you memorized, all of that came from a book written in Alexandria 2,300 years ago by a man about whom we know almost nothing. That absence of biographical detail starts to feel less like a gap in the historical record and more like a kind of perfection. What could we add to Euclid's story that would matter more than the elements itself? What personal details would make his achievement more impressive or his influence more profound? The work speaks. The man can remain silent, but the Elements was never meant to stand alone. Euclid wrote other works, most of them lost, that explored territories his famous textbook couldn't reach. We know their titles, we know roughly what they contained, and what survives tells us something crucial about how the Greeks thought mathematics should work. There was the data, a collection of problems about determining geometric quantities from given information. It was a supplement to the Elements, showing how to apply the basic theorems to more complex situations. Only fragments remain, but medieval mathematicians still studied it as an advanced text. Then came the optics, and this is where things get interesting. Euclid wrote about light and vision, using the same geometric method he'd applied to circles and triangles. He assumed light travels in straight lines. He analysed how objects appear at different distances. He explained perspective. The approach was pure geometry applied to physical phenomena, showing that the mathematical method could extend beyond abstract shapes into the real world. The phenomena took this further. It applied geometry to astronomy, explaining how the sphere of stars appears to rotate around the Earth. Whether Euclid actually believed in a geocentric universe, or was just describing appearances, we don't know. What matters is the technique. Celestial movements could be analysed geometrically. The heavens obeyed the same logical principles as earthly figures. Most intriguing was a work called the Porisms. It's completely lost. We know it existed because later mathematicians mention it, sometimes with awe. Pappus, writing 600 years after Euclid, said the Porisms was exceptionally subtle and contained propositions that were hard even to classify. They weren't quite theorems and weren't quite problems. They were something in between, some new kind of mathematical statement. Modern scholars have tried to reconstruct what the Porisms might have contained based on hints in later texts. The consensus is that they dealt with advanced properties of geometric figures, possibly related to what we now call projective geometry. But we're guessing. The work is gone. What survived instead was the data, the optics, and fragments of other treatises, enough to show that Euclid's genius wasn't limited to one domain. He could take the geometric method and apply it anywhere rational analysis was possible. This versatility mattered. It meant geometry wasn't just a subject. It was a way of thinking, a tool that could unlock understanding in any field that involved space, proportion, or logical relationship. Consider what this meant for someone in the ancient world trying to understand their universe. If you wanted to know why a stick appears to bend when placed in water, geometry could help. If you wanted to predict where a planet would appear in the sky next month, geometry was your tool. If you wanted to design a building that wouldn't collapse, geometric principles guided you. The Elements gave you the foundation. The other works showed you how to build on it. Together, they represented a complete system for mathematical reasoning about the world. But here's where we need to pause and acknowledge something that makes modern mathematicians uncomfortable. Euclid was wrong about some things. Not in his proofs, those are valid, but in his assumptions about what geometry describes. For 2,000 years, people believed Euclidean geometry described the actual structure of space. That parallel lines never meet wasn't just a logical consequence of certain axioms. It was how space really worked. The angles of a triangle really did add up to exactly 180 degrees. The Pythagorean theorem really did describe the relationship between the sides of any right triangle in the real world. Then in the 19th century, mathematicians started asking uncomfortable questions. What if you changed the parallel postulate? What if you assumed that through a point not on a line, you could draw 0 parallel lines, or infinitely many? What geometries would result? The answer was shocking. You got perfectly consistent mathematical systems. Non-Euclidean geometries that obeyed different rules, but were just as logically coherent as Euclid's. On curved surfaces, triangles could have more than 180 degrees. Parallel lines could converge. Everything Euclid had assumed about space turned out to be just one possibility among many. Worse, when Einstein developed general relativity, he showed that space itself is curved by gravity. The geometry of the actual universe isn't Euclidean. Light doesn't travel in perfectly straight lines. The angles of a cosmic triangle don't add up the way Euclid said they should. Does this mean the Elements is obsolete? Absolutely not. Here's what happened instead. Mathematics separated itself from physical space. Geometry became understood not as the study of actual space, but as the logical consequences of certain axioms. You could choose your axioms and see where they led. Euclidean geometry was one system. Non-Euclidean geometries were others. All were equally valid as mathematics. The elements became even more important in this new understanding because it demonstrated the method perfectly. It showed how to build an entire mathematical world from a handful of starting assumptions. The specific assumptions Euclid chose turned out not to describe physical reality exactly, but the approach, the axiomatic method, became the gold standard for all mathematics. Every modern mathematical field now works this way. You start with axioms, you derive theorems, you build systems, group theory, topology, abstract algebra, all of them follow the pattern Euclid established. The content has changed beyond recognition, but the method remains. And for practical purposes, Euclidean geometry is still exactly right. If you're building a house, Euclid's theorems work perfectly. The curvature of space is so tiny at human scales that you'd never notice it. The carpenter using the Pythagorean theorem to check if a corner is square is applying mathematics that's just as valid today as it was in Alexandria. So we have this strange situation where Euclid's geometry is simultaneously outdated and eternal. Outdated as a description of cosmic space, eternal as a logical system and as a practical tool for everyday problems. The Elements survives not because it's the final word on geometry, but because it taught us how to think mathematically. It showed that you could take a few simple ideas and, through pure reason, build something vast and certain. That lesson doesn't depend on whether space is curved or flat, but there's another element to Euclid's influence that's even stranger. His work helped create the idea that mathematics discovers truth rather than inventing it. When you work through a Euclidean proof, it doesn't feel like you're constructing something arbitrary. It feels like you're uncovering something that was already there, waiting to be found. Take the Pythagorean theorem. Once you accept Euclid's axioms, the theorem follows necessarily. You're not deciding that it's true. You're recognizing that it must be true. The mathematics seems to exist independent of human minds. In some abstract realm where triangles and circles have properties whether anyone discovers them or not. This Platonic view of mathematics, the idea that mathematical objects are real in some sense, existing outside space and time, became deeply embedded in Western thought. It's not the only possible view. You could argue that mathematics is just a human invention, a useful fiction we've created. But for most people who actually do mathematics, it feels like discovery. The theorems seem to be already true, waiting for us to find them. Euclid's elements reinforce this feeling because the proofs are so inevitable. You can't argue with them. You can't negotiate. Once you grant the axioms, everything else follows with perfect necessity. That sense of mathematical truth, as absolute and unchanging, became part of how European culture understood knowledge itself. Which brings us to an uncomfortable question. Did this do more harm than good? On one hand, the Euclidean model of certain knowledge, built from first principles, inspired centuries of intellectual progress. It gave us confidence that the universe could be understood rationally. It suggested that other fields might achieve the same certainty as geometry if they adopted the same methods. On the other hand, it created impossible expectations. Philosophy, ethics, politics, none of these fields can actually work like geometry. They deal with matters where axioms aren't self-evident and where reasonable people can disagree on fundamentals. The attempt to achieve geometric certainty in areas where it's not possible led to rigid systems and false confidence. Descartes wanted to rebuild all knowledge using the geometric method. He failed. Spinoza tried to do ethics like Euclid did geometry, with axioms and proofs. It didn't work. The Euclidean ideal of absolute certainty became a burden when applied to domains it couldn't handle. Maybe that's unfair to Euclid. He never claimed his method applied to everything. He just used it for geometry because that's where it worked. The overreach was committed by later thinkers who wanted to import mathematical certainty into fields that couldn't support it. Still, the influence was real. The elements shaped not just mathematics, but expectations about what knowledge should look like. It created a standard that other fields have spent centuries either trying to meet or learning to abandon. And here's what's remarkable. Despite all these complications, despite the discovery of non-Euclidean geometries and the limits of the axiomatic method in other fields, the elements itself remains exactly as valid as it ever was. The proofs still work, the theorems are still true within the system. Nothing we've learned in 2300 years has made proposition 1 false or rendered the Pythagorean theorem incorrect. The book is frozen. It reached a kind of perfection where nothing can be added or removed. You can't improve Euclid's proof that there are infinitely many primes. You can give different proofs, perhaps shorter ones, but his proof stands complete. It proved what it set out to prove, and that's finished. This permanence is unusual. Most ancient works that survive are interesting as historical documents, but outdated as actual content. We study Aristotle's physics as history of science, not as science. We read ancient medical texts as curiosities, but we study Euclid's elements as mathematics. It's still teaching the same lessons it taught in Alexandria. Open a modern geometry textbook. The notation will be different. The presentation might be updated, but the fundamental content, the theorems, the proofs, the logical structure, comes straight from Euclid. Teachers still assign problems about inscribing circles in triangles. Students still prove that base angles of isosceles triangles are equal. The subject hasn't been replaced, it's been preserved. Why? Because Euclid captured something essential about geometric relationships, and he captured it in a form that can't be improved. You can add to geometry. There are vast branches of the subject he never touched, but you can't redo what he did better than he did it. That's a rare achievement in any field. To do something so thoroughly, so clearly, so completely that no one needs to do it again. To solve problems that stay solved. The elements represents 2,000 years of mathematical stability. While science revolutionized itself repeatedly, while philosophy moved through countless schools and fashions, Euclidean geometry remained essentially unchanged. Students in Newton's time learned the same geometry as students in Ptolemy's time. The notation evolved, but the substance held. Only in the 19th century did mathematics finally grow beyond Euclid's framework. And even then, the growth was extension, not replacement. Non-Euclidean geometry didn't erase Euclidean geometry. It added alternatives. The elements remained the starting point, the baseline, the thing every mathematician learned first. This stability gave mathematics an authority that other fields couldn't claim. When mathematicians said something was proven, it stayed proven. The certainty was real, at least within the bounds of their axioms. That authority shaped how society viewed mathematical reasoning and how scientists approached their work. But we should be careful about celebrating permanence too much. The fact that Euclidean geometry didn't change for 2,000 years also meant that mathematical progress in that area was frozen. Sometimes fields need disruption. They need people to question the foundations and imagine alternatives. The breakthrough to non-Euclidean geometry only happened when mathematicians finally dared to challenge Euclid's parallel postulate. For centuries, people had tried to prove it from the other axioms, assuming it must be derivable. The revolutionary step was recognizing that it was independent, that you could deny it and still have consistent mathematics. That took courage because Euclid's authority was so complete. To suggest that his geometry wasn't the only geometry felt almost blasphemous. The elements had achieved such perfection that questioning it seemed pointless. Yet that permanence also protected mathematics during periods when other fields were vulnerable. When religious authorities prosecuted scientists for contradicting scripture, mathematicians worked in relative safety. No pope could declare Euclidean geometry heretical. The theorems didn't make claims about the physical universe that could conflict with doctrine. They were pure logic, operating in an abstract space that theology couldn't touch. This gave mathematics a strange privilege. While astronomers faced inquisitions and natural philosophers navigated dangerous waters, geometers could pursue their work without looking over their shoulders. The subject was politically neutral, theologically safe, philosophically abstract. You could be Christian, Muslim, Jewish, or anything else, and still agree on the properties of triangles. That universality helped mathematics cross cultural boundaries more easily than other forms of knowledge. When Islamic scholars encountered Greek mathematics, they didn't reject it as pagan learning. They recognized it as true regardless of who had discovered it. A theorem proved in Athens was equally valid in Baghdad. The logic transcended culture. So Arabic translations of the elements preserved Euclid through centuries, when the original Greek texts were lost to Western Europe. Scholars in the House of Wisdom studied geometry using the same axioms and proofs that had been taught in Alexandria. They added their own discoveries, extending Euclid's work, but they honoured his foundation. When these texts eventually returned to Europe through Latin translations, they carried the accumulated insights of multiple civilizations. The elements that medieval European scholars studied had been annotated by Greek, Arabic, and Persian commentators. Each tradition had added something, but all had preserved the core. This is unusual. Most ancient knowledge doesn't travel well across cultural boundaries. Religious texts get reinterpreted, philosophical ideas get transformed, scientific theories get replaced. But mathematical proofs have a portability that other forms of knowledge lack. If the logic is sound, it works everywhere. Euclid's influence on education was equally profound. For centuries, studying the elements was the standard introduction to rigorous thinking. Students learned geometry not just to understand shapes, but to develop logical reasoning. The subject trained minds. The pedagogical method was distinctive. You didn't just memorize facts about triangles. You worked through proofs step by step, seeing how each conclusion followed necessarily from what came before. This taught a way of thinking that transferred to other domains: legal reasoning, philosophical argument, scientific investigation, all borrowed from the geometric method. Consider Abraham Lincoln, who read Euclid as an adult to sharpen his logical faculties. He wasn't planning to become a geometer. He wanted to strengthen his argumentative skills for law and politics. The elements served that purpose because its method of proof was so clear and rigorous. If you could follow Euclid's reasoning, you could construct tight arguments in any field. This made geometry central to classical education for 2,000 years. It wasn't vocational training. Most students would never use geometric theorems in their daily work, but they would use the mental discipline that geometry developed. They would carry forward the habit of demanding proof, of checking assumptions, of building conclusions carefully from foundations. The danger, of course, was that this emphasis on geometry could make mathematics seem synonymous with Euclidean geometry. Students learned to think that mathematics was about shapes, angles, and spatial relationships. The broader possibilities of mathematical thinking, algebra, probability, analysis, took much longer to enter the curriculum. Still, starting with geometry had advantages. The subject is visual in a way that makes it accessible. You can draw the figures, see the relationships, develop geometric intuition. Abstract algebra or calculus are harder to visualize. They require more sophisticated preparation. Euclid gave students an entry point into mathematical reasoning that felt concrete while actually being quite abstract. Yes, you're drawing triangles, but you're also learning how to construct deductive arguments from axioms. That's sophisticated intellectual work disguised as something simple. The elements also established a template for how mathematical knowledge should be presented. Other mathematicians imitated Euclid's axiomatic approach, starting with definitions and basic assumptions and building systematically from there. This became the gold standard for mathematical exposition. When Newton wrote the Principia, he organized it geometrically, even though his actual methods involved calculus. He presented his physics in the style of Euclidean geometry because that gave his work authority. Readers trusted geometric proof. They knew how to evaluate it. Newton was borrowing Euclid's credibility. Spinoza went further, organizing his philosophy as if it were geometry. Ethics demonstrated in geometrical order, starts with axioms and definitions, then derives propositions like theorems. He wanted philosophical conclusions to have the same necessity as geometric ones. Whether that works is debatable, but the ambition shows how influential Euclid's method had become. People wanted the certainty that geometry offered. They wanted to prove things rather than just argue about them. Euclid had shown that certain knowledge was possible in mathematics. Could the same method yield certainty in other domains? Probably not. The strength of geometric proof comes from working within carefully defined constraints. You accept the axioms, you follow the rules of logic, you reach necessary conclusions. But most interesting questions in philosophy, science, or ethics don't fit into that framework. The axioms aren't self-evident. The definitions aren't clear-cut. The logic alone can't settle the matter. But the dream persisted. If we could just find the right axioms, the right starting points, maybe we could turn messy subjects into precise sciences. Euclid had done it for geometry. Someone else might do it for physics or psychology or political theory. That dream drove much of Enlightenment thought. Thinkers believed that human knowledge could be systematized, organized into clear principles from which everything else followed. Euclid was the model. His elements showed what was possible when a subject was properly organized. The reality turned out to be more complicated. Most fields resisted complete axiomatization. Even mathematics itself proved harder to systematize than Euclid's success suggested. Geometry was the easy case because its basic objects, points, lines, planes, are simple, and its fundamental relationships are clear. Other branches of mathematics dealt with more complex structures. The attempt to give arithmetic a rigorous foundation comparable to Euclid's geometry, took 2,000 years and revealed unexpected difficulties. Gödel's incompleteness theorems eventually showed that complete axiomatization of arithmetic was impossible. There would always be true statements that couldn't be proved within the system. So Euclid's achievement was both more and less than it seemed. More because he created something genuinely lasting and influential. Less because it represented a special case rather than a universal method. Geometry allowed for the kind of systematic treatment he gave it. Not everything does. Still, the elements remained the exemplar. When mathematicians wanted to show that they had organized a subject properly, they reached for Euclidean presentation. When philosophers wanted to claim certainty for their conclusions, they imitated geometric proof. The influence was pervasive even when the imitation didn't quite work. And within mathematics itself, Euclid's legacy shaped how the discipline developed. The axiomatic method became standard. Mathematicians learned to identify basic assumptions, define terms precisely, and build carefully from foundations. This created a culture of rigor that distinguished mathematics from other fields. You can see this in how mathematical papers are written. They don't just assert results, they prove them from established principles. The proof is the point. A brilliant conjecture without proof is just a guess. A mundane result with rigorous proof is mathematics. That standard traces back to Euclid. He established the expectation that mathematical claims must be justified through logical demonstration. His proofs set the bar for what counted as adequate justification. Later, mathematicians had to meet or exceed that standard. This created continuity across centuries. A modern mathematician reading Euclid recognizes the enterprise as fundamentally the same as contemporary mathematics. The problems are different, the notation has evolved, but the commitment to proof remains constant. Compare this to physics, where reading Newton feels like reading ancient history. His conceptual framework has been replaced multiple times. Or philosophy, where reading Plato requires extensive historical contextualization. Mathematics has changed less because Euclid established foundations that actually held. Of course, mathematics has grown enormously beyond what Euclid knew. Entire fields he never imagined now exist. But his work remains part of the living tradition rather than mere historical background. Mathematicians still care about the problems he solved and the methods he used. This is particularly striking given how old the Elements is. We're talking about a text from the 3rd century BC that's still actively used in education. How many other works can claim that? Not many. Most ancient texts are studied by specialists, not taught to teenagers. But walk into a high school geometry class anywhere in the world and you'll find students learning Euclidean geometry. Maybe they're using different terminology. Maybe they're drawing on computers instead of with compass and straightedge. But they're learning the same subject that students learned in Alexandria. That's extraordinary when you think about it. A 2,300-year-old curriculum still functioning, still teaching effectively, still introducing students to mathematical reasoning through the same logical structures. Why has this survived when so much else hasn't? Part of it is the inherent stability of mathematical truth. Correct proofs don't age. Part of it is the pedagogical effectiveness of geometry as an introduction to logic. Part of it is institutional inertia. Education systems are slow to change, and the Elements had been standard for so long that replacing it was difficult. But perhaps the deepest reason is that Euclid solved a problem that stays solved. How do you teach people to think rigorously? How do you develop logical reasoning? How do you show students what proof means? The Elements answers these questions better than most alternatives, not because it's the only possible answer, but because it's a very good answer that has the advantage of being thoroughly tested. Generations of teachers know how to teach it. Generations of students have learnt from it. Innovation is valuable, but so is preservation. Mathematics benefits from having a stable core that everyone learns, a common foundation that ensures mathematicians can communicate with each other. Euclid provides that foundation. The danger is stagnation. If geometry education never evolves beyond Euclid, it can't incorporate newer insights or address modern needs. Some educational reformers have argued for replacing Euclidean geometry with other topics, statistics, probability, discrete mathematics, that might be more relevant to contemporary life. There's merit to that argument. Most people won't use geometric proofs after high school, but they will encounter statistical claims and probabilistic reasoning. Maybe education should shift accordingly. On the other hand, geometry offers something those subjects struggle to provide: a clear introduction to deductive proof. Statistics and probability are important but messier. They don't have the same clean logical structure. Starting with them might leave students without the foundation that geometry provides. This tension remains unresolved. Educational systems continue to teach Euclidean geometry while also trying to make room for newer mathematical topics. The Elements hasn't been displaced, but it's sharing space with subjects Euclid never knew. That seems right. Honor the tradition without being imprisoned by it. Learn from Euclid's methods while recognizing that mathematics has grown beyond his scope. Use the Elements as a starting point, not an ending point. But here's what we should recognize: the fact that we're still having this conversation, still deciding how much Euclid to teach, still using his work as the baseline against which alternatives are measured. That shows how successful the Elements was. Most works from antiquity are curiosities. We study them to understand history, not to learn current knowledge. The Elements is different. It's still teaching, still shaping minds, still introducing students to mathematical proof of. That makes Euclid not just historically important, but presently relevant. His work isn't finished influencing mathematics. It's still active in classrooms, still forming the way people learn to think logically, still serving as the foundation on which further mathematical education builds. And that influence extends beyond the classroom. The Elements shaped how we think about knowledge itself. Consider what Euclid demonstrated. You can start with a handful of simple statements that everyone accepts. From those using pure logic, you can build an entire edifice of knowledge. Every conclusion proven, every step justified. No gaps, no leaps of faith. Just relentless, careful reasoning from foundation to completion. This is the axiomatic method. It became the model for how knowledge should be organized. Philosophers saw what Euclid had done and wondered, could we do this for ethics, for politics, for all human knowledge? Could we find the basic axioms of morality and derive everything else from them? Could we discover the fundamental principles of good government and reason our way to the perfect society? This wasn't idle speculation. Serious thinkers devoted their lives to this project. Spinoza wrote his Ethics in geometric form, complete with axioms, propositions, and proofs. He believed moral truth could be demonstrated with the same certainty as geometric truth. The book looks like Euclid: definitions, axioms, theorems. He's trying to build ethics the way Euclid built geometry. Did it work? That's debatable. Spinoza's Ethics is brilliant, but whether it achieves geometric certainty about morality is questionable. Human behavior is messier than triangles. Moral axioms are harder to agree on than geometric ones. But the attempt reveals something important. Euclid had shown that systematic, rigorous knowledge was possible, that you could start with basics and build something certain and complete. That influenced how people thought about knowledge in every field. The scientific revolution carried Euclidean echoes throughout. Newton's Principia Mathematica, the book that laid out the laws of motion and universal gravitation, was written in geometric form. Newton proved his physics theorems like geometric propositions. He was following Euclid's template. Why? Because Euclid had demonstrated what rigorous proof looked like. If you wanted your work to be taken seriously as certain knowledge, you modelled it on the elements. You stated your axioms clearly. You proved your theorems carefully. You showed your reasoning step by step. This became the standard of intellectual rigor. Not everyone could meet it. Most fields aren't suited to the geometric method. History doesn't have axioms. Literature doesn't proceed by proof. But the aspiration toward Euclidean certainty shaped intellectual culture for centuries. If you couldn't achieve it, you at least acknowledged it as the ideal. The Enlightenment was soaked in this. Thinkers believed that reason, properly applied, could solve all problems. They'd seen what mathematics could accomplish. Surely, the same methods could illuminate everything else. Just find the right axioms. Apply logic correctly. The answers would follow. This was optimistic. Perhaps too optimistic. Reality proved more complicated than geometry. But the confidence came from Euclid. He'd shown what systematic thinking could achieve. Even when fields moved away from the geometric method, they retained something Euclidean: the insistence on clear definitions, the demand for explicit reasoning, the recognition that you need solid foundations before building complex arguments. These are Euclidean inheritances. Modern mathematics has moved far beyond Euclid's methods. We don't organize mathematics axiomatically the way he did anymore. We use different logical frameworks. We accept different standards of proof. We work in abstract spaces Euclid never imagined. But we still value what he valued: clarity, rigor, logical necessity, the conviction that mathematical truth must be demonstrated, not merely asserted. Those values came from somewhere. They weren't inevitable. Other cultures developed mathematics without the same emphasis on proof. Chinese mathematics achieved remarkable results through algorithmic methods without Euclidean-style demonstration. Indian mathematics made profound discoveries while maintaining different standards of justification. The Greek insistence on proof, crystallized in Euclid, became the Western mathematical tradition. And as Western mathematics spread globally, it carried Euclidean values with it. Now those values are simply considered how mathematics works. But they have a history. They came from choices the Greeks made about what mathematics should be. Euclid codified those choices. Here's something else the elements did. It made mathematics seem perfect. Geometry, as Euclid presented it, appeared flawless. A complete, self-contained system, with no gaps, no contradictions, no uncertainties, everything proven, everything certain, a monument to human reason's power. That appearance was deceptive. The elements has flaws. Euclid assumed things he didn't state explicitly. His axioms don't actually cover everything his proofs require. Careful analysis reveals gaps in his logic. But for 2,000 years, most readers didn't notice. They saw perfection. And that shaped their understanding of what mathematics was. It was the one domain where humans achieved absolute certainty, where truth was eternal and unchanging, where reason reigned supreme. This created unrealistic expectations. Mathematics isn't actually perfect. It's a human activity, subject to error and revision like everything else. But Euclid made it seem perfect. That influenced how people thought about mathematical authority. When mathematicians proved something, people believed it absolutely. Mathematics was the standard of certainty. As certain as a mathematical proof became the highest compliment you could pay to an argument. That's still true today. We trust mathematics in ways we trust almost nothing else. Scientific theories get revised, historical accounts get questioned, philosophical arguments remain debatable. But mathematical proofs, once proven, they stay proven. That confidence comes partly from Euclid. He demonstrated that mathematical certainty was achievable. He built something that seemed unshakable. Even after we discovered the flaws, even after we realized his system wasn't as perfect as it appeared, we retained the conviction that mathematics could achieve certainty. We just needed to be more careful than Euclid was. The 19th century brought a reckoning. Mathematicians began examining Euclid's foundations with unprecedented scrutiny. They found the gaps, they discovered the hidden assumptions. They realized that the Elements, for all its brilliance, wasn't rigorous by modern standards. This could have been devastating. It could have undermined faith in mathematical proof. Instead, it led to a deepening of mathematical rigor. Mathematicians set out to do what Euclid had attempted, but do it better. Identify every assumption, state every axiom explicitly, eliminate every gap in logic. This project culminated in the work of David Hilbert, who published his Foundations of Geometry in 1899. Hilbert presented a genuinely rigorous axiomatization of Euclidean geometry. Every assumption stated, every proof gap filled. It was Euclid done right. But notice what Hilbert was doing. He wasn't abandoning Euclid, he was perfecting him. The goal was still a complete axiomatic system for geometry. The method was still logical deduction from stated principles. The vision was still Euclidean. Hilbert just executed it more carefully. That's how Euclid's influence works. Even when we move beyond him, we're often moving in directions he pointed. We're trying to achieve what he attempted, just more thoroughly. The 20th century brought another development. Non-Euclidean geometry became not just mathematically interesting, but physically relevant. Einstein's general relativity describes gravity as the curvature of space-time. The geometry of the universe, according to Einstein, is non-Euclidean. This was profound. Euclid's geometry wasn't just incomplete or flawed, it was wrong about physical space. The parallel postulate, that troublesome fifth axiom, is false in the actual universe we inhabit. Did this diminish Euclid's achievement? Not really. It showed that the Elements describes an idealized, abstract space rather than physical reality. But mathematics had already been moving in that direction. By the time Einstein came along, mathematicians understood geometry as the study of abstract structures, not necessarily the description of physical space. Euclid had thought he was describing reality. We now know he was describing one possible mathematical structure. But that doesn't make his work less valuable. It makes it differently valuable. The Elements isn't physics, it's pure mathematics. And as pure mathematics, it remains correct within its own framework. Physical space might be curved, but Euclidean geometry is still the geometry of flat space. And flat space, even if not physically real, is mathematically important. Engineering uses Euclidean geometry because at human scales, space is flat enough. Architecture assumes Euclidean principles because buildings are small compared to cosmic curvature. Computer graphics uses Euclidean geometry because screens are flat. So even after Einstein, even after we learned that physical space curves, Euclid remains practically relevant. His geometry is the geometry of the everyday, the geometry of the human scale, the geometry that works for ordinary purposes. That's a kind of vindication, not because Euclid was right about ultimate reality, but because he was right about the mathematics we need for most purposes. His abstraction, even if not physically accurate at cosmic scales, is useful at the scales where humans live and build and create. And beyond practical usefulness, there's aesthetic value. Euclidean geometry is beautiful. The proofs are elegant, the structure is harmonious, the whole system fits together with satisfying completeness. Mathematicians study it not because they believe it describes the universe, but because it's worth knowing for its own sake. Music doesn't have to serve a practical purpose to be valuable. Art doesn't have to be useful to matter. Mathematics can be appreciated aesthetically, and Euclidean geometry is one of mathematics' great aesthetic achievements. The Elements is worth reading the way a classic novel is worth reading. Not for information you'll use, but for the experience of encountering something beautifully constructed. Students sometimes struggle with this. They want to know why they're learning geometry. What's the point if it's not even how space actually works? The answer isn't always satisfying. You're learning it because it's worth knowing, because it teaches you to think clearly, because it's part of your intellectual heritage, because encountering well-organized thought is valuable. Those are real reasons, even if not immediately practical. Education isn't just job training, it's also cultivation of the mind. Euclid cultivates logical thinking, appreciation for proof, and understanding of mathematical structure. Those are worthwhile even if you never calculate another triangle after graduation. But there's something else happening when students learn Euclidean geometry. They're joining a tradition. They're reading the same text, working through the same proofs, encountering the same ideas that students have engaged with for millennia. That creates continuity across time. A student today proving the Pythagorean theorem is doing what students did in medieval universities, Renaissance academies, Enlightenment schools. Different languages, different countries, different centuries, but the same mathematics, the same logical steps, the same moment of understanding when the proof clicks into place. That's rare. How many human activities connect us so directly to the distant past? Most of what we do would be unrecognizable to people from earlier eras, but mathematics transcends historical difference. A proof is a proof. A theorem is a theorem. Euclid speaks across the centuries because mathematical truth doesn't change. This gives mathematics a peculiar timelessness. History is always being rewritten as we discover new evidence or develop new interpretations. Science constantly revises its theories as new data emerges. Philosophy remains perpetually unsettled, with questions debated endlessly without resolution. Mathematics accumulates, new theorems get proven, new fields develop, but the old results don't get discarded, they get incorporated. Euclid's theorems are still true. We just understand them more deeply now, see them in broader context, recognize their relationship to other mathematical structures. The element sits in mathematical history like a foundation stone. Everything built afterward rests on it, even when that later work extends far beyond what Euclid imagined. You can trace lines of development from his axioms to the most abstract modern mathematics. The connection is there. That makes Euclid more than historically important. He's mathematically ancestral. Modern mathematics has Euclidean DNA. The values, the methods, the standards, they descend from him. Modified, certainly, extended absolutely, but recognizably related, and that influence continues forward. Students learning geometry today are being shaped by Euclid's approach. Their understanding of what proof means, what mathematics is, how logical thinking works. It's all downstream from the elements. They might never read Euclid directly. Doesn't matter. They're learning Euclidean mathematics, thinking Euclidean thoughts, following Euclidean methods. The elements is still active in the world, still teaching, still shaping minds. Not as a museum piece we admire from a distance, but as a living force in mathematical education and culture. Euclid isn't past, he's present. His work continues working, continues influencing, continues mattering. That staying power reveals something deeper about what Euclid actually accomplished. He didn't just write a mathematics textbook, he created a template for how humans organize and transmit knowledge. Before Euclid, mathematics existed as scattered results, clever solutions to specific problems, useful techniques passed between practitioners, isolated insights without clear connections. What he did was revolutionary. He showed that all these separate pieces could be organized into a unified system, built from foundational principles through pure logic. That's the real innovation. Not any particular theorem, but the systematic approach. The idea that you could start with a few simple assumptions and derive an entire field of knowledge through careful reasoning. That you could organize complexity into clarity. That you could make knowledge teachable by making it logical. This approach became the model for every science that came after. When Newton wanted to explain how the universe worked, he didn't just describe his observations. He wrote the Principia in geometric form, mimicking Euclid's structure. Definitions, axioms, propositions, proofs. The same architecture. He was saying, this is serious knowledge, organized like Euclid organized geometry. When philosophers wanted to establish certain knowledge, they reached for the same template. Spinoza wrote his Ethics as a geometric system. Definitions, axioms, propositions, demonstrations. He was trying to do for philosophy what Euclid did for geometry. Build certainty from foundations through pure logic. It didn't always work. Philosophy and physics aren't quite like geometry. Their foundations aren't as secure. Their logic isn't as airtight. But the attempt reveals how influential Euclid's method became. For centuries, if you wanted your knowledge to be taken seriously, you tried to make it look like the elements. That influence extended beyond academia into how people thought about knowledge itself. The Euclidean ideal suggested that true understanding meant reducing complexity to simplicity, finding the basic principles, deriving everything else logically, building systems that were complete, consistent, elegant. This shaped education. Students learned to value systematic thinking, logical progression, rigorous proof. They learned that real knowledge wasn't just accumulating facts, but understanding how facts connected, how they followed from principles, how they formed coherent structures. Those values went deep into Western culture. The expectation that arguments should be logical, the preference for clear definitions, the demand for evidence and reasoning, the skepticism toward claims that couldn't be demonstrated. All of this has Euclidean roots. You see it in law, where cases are built through logical argument from established principles, in architecture, where structures follow geometric principles, in music theory, where harmony gets explained through mathematical ratios, in computer programming, where systems get built from basic operations through logical steps. The Euclidean approach: define your terms, state your assumptions, derive your conclusions, became the default template for rigorous thinking across disciplines. Not because Euclid invented logic, but because he demonstrated so convincingly what logical organization could achieve. And yet there's irony here. The same work that established this template for certain knowledge eventually revealed the limits of that certainty. The parallel postulate, that troublesome fifth axiom, turned out to be the crack in the foundation. For 2,000 years, mathematicians tried to prove it from the other axioms. They all failed. Eventually, in the 19th century, mathematicians realized why. It couldn't be proven. It was genuinely independent. That realization led to non-Euclidean geometries, mathematical systems where the parallel postulate didn't hold, but everything else remained consistent. These weren't just curiosities. They were complete, rigorous geometries, every bit as logical as Euclid's. They just described different kinds of space. This discovery was philosophically shocking. It meant geometry wasn't about discovering the one true structure of space. It was about exploring different possible structures. Mathematics wasn't uncovering pre-existing truth. It was creating consistent systems. Einstein made this concrete. General relativity describes gravity using non-Euclidean geometry. Space near massive objects curves. Parallel lines can converge. The universe itself doesn't follow Euclid's rules. Does this make Euclid wrong? Not exactly. His geometry still works perfectly for everyday situations. It's still how we build buildings, measure land, navigate locally. It's just not the only possible geometry, and it's not the geometry of the universe at large scales. But here's what's remarkable. This discovery didn't diminish Euclid's achievement. It revealed it more fully. What he'd really done was create the first complete axiomatic system, the first demonstration that you could build mathematics from explicit foundations through pure logic. The parallel postulate controversy didn't show Euclid failed. It showed he succeeded so well that mathematicians could use his methods to go beyond him. Non-Euclidean geometry exists because Euclid established how axiomatic geometry should work. The 19th century geometers who developed these new systems were following Euclidean method even while contradicting Euclidean content. They kept his approach while changing his assumptions. That's ultimate influence. When your method becomes the tool people use to move beyond your conclusions, you've really changed how humans think. Modern mathematics has taken this further than Euclid could have imagined. Axiomatic systems now exist for all kinds of mathematical structures. Group theory, topology, set theory, category theory, all built like Euclid built geometry. State your axioms, derive your theorems, prove your results rigorously. The elements established the template. Everything since has been elaboration. But there's a tension here worth examining. Mathematics has become increasingly abstract. Modern mathematicians study objects that have no physical interpretation. They prove theorems about structures that exist only in logical space. This seems far from Euclid's geometry of lines and circles, triangles and squares. Yet the connection remains. Those abstract structures are still built axiomatically, still proven rigorously, still organized systematically. The form is Euclidean even when the content isn't. And sometimes the content circles back too. Euclidean geometry keeps reappearing in unexpected places. Computer graphics use it constantly. Game engines render three-dimensional worlds using geometric transformations that Euclid would recognize. GPS systems calculate positions using geometric principles. Architects and engineers still work primarily in Euclidean space. Even in physics, where space-time is non-Euclidean, local regions are approximately Euclidean. Zoom in enough and space looks flat. Euclid's geometry remains the local approximation, the everyday reality, even if the global structure is different. So we live in this strange situation where Euclidean geometry is simultaneously superseded and indispensable. We know it's not the deepest truth about space. We use it constantly anyway. It's the mathematics of human scale, of the world we directly inhabit. That practical durability matters. The Elements wasn't written for abstract contemplation. It was practical mathematics for practical purposes. Land surveying, architecture, navigation, commerce. The theorems had applications. The proofs ensured reliability. That combination of rigor and utility is rare. Most practical mathematics is approximate. Most rigorous mathematics is impractical. Euclid managed both. His geometry was precise enough for theoretical satisfaction and useful enough for real work. This dual nature helps explain the Elements' longevity. It satisfied both mathematicians and practitioners. Scholars could admire its logical perfection. Craftsmen could use its results. Teachers could present it as both intellectually beautiful and practically valuable. Students got something similar. They learned to think clearly while learning useful skills. The geometry wasn't just mental exercise, it connected to the physical world. You could see triangles, draw circles, measure angles. The abstractions had concrete reference. Modern mathematics has lost some of this. Advanced courses deal with objects that have no physical representation. Students struggle to connect abstract definitions to anything tangible. The mathematics becomes purely symbolic manipulation. There's value in abstraction. Modern mathematics needs it. But there's also loss. The connection between mathematical ideas and physical intuition weakens. Mathematics becomes less accessible, more forbidding. Euclidean geometry retains that connection. You can draw it, you can build it, you can see it around you. That makes it pedagogically powerful. It's abstract enough to teach rigorous thinking, but concrete enough to stay grounded. This is why geometry remains in the curriculum despite being ancient. Not because students will use those specific theorems, but because geometry teaches mathematical thinking in a uniquely accessible way. The visual nature helps. The logical structure helps. The historical weight helps. When students prove the Pythagorean theorem, they're not just learning a relationship between sides of right triangles. They're learning what mathematical proof means. They're experiencing the satisfaction of logical certainty. They're joining a tradition of mathematical thought, stretching back millennia. That's worth something. In an age of calculators and computers, mathematical education isn't about computation. It's about understanding, about learning to think precisely, about developing logical intuition. Euclidean geometry teaches those things well. The proofs are genuine proofs, rigorous and compelling. But they're also accessible. A high school student can understand them, can follow the logic, can experience that click of insight when the argument becomes clear. That accessibility matters enormously for mathematics as a culture. If only specialists could understand mathematical reasoning, mathematics would become esoteric. By keeping Euclidean geometry in the curriculum, we maintain a shared mathematical language, a common foundation that educated people can reference. When someone says QED after making an argument, they're invoking Euclidean tradition. When someone demands proof rather than assertion, they're applying Euclidean standards. When someone values logical consistency, they're honoring Euclidean values. These cultural traces matter. They shape how societies think about truth, evidence, and reasoning. They create expectations for public discourse. They establish standards for legitimate knowledge. Euclid contributed to that in ways that extend far beyond mathematics. The elements demonstrated that certain knowledge was possible through pure reason, that complex truths could be derived from simple principles, that logical argument could compel agreement. These ideas became foundational to Western intellectual culture. The scientific revolution built on them. The Enlightenment extended them. Modern democracy assumes them. We expect claims to be supported by evidence and logic. We distrust assertions that can't be demonstrated. We value systematic thinking over chaotic intuition. Not all of this comes from Euclid, obviously, but he provided a powerful early model. He showed what rigorous knowledge looked like. He demonstrated that human reason could achieve certainty about abstract truths. That demonstration has echoed through history. Every time someone constructs a careful argument from premises to conclusion, they're working in Euclid's shadow. Every time someone demands logical consistency, they're applying Euclidean standards. Every time someone builds systematic knowledge, they're following Euclidean example. The influence is so pervasive, it's almost invisible. We don't think I'm being Euclidean when we reason logically. We just reason logically. The approach has become natural, automatic, assumed, but it wasn't always natural. It had to be established. Someone had to show that this was how knowledge should be organized. That logical demonstration was superior to received wisdom or authoritative decree. Euclid did that. The Elements was the proof of concept for rational knowledge. It showed that systematic organization and rigorous proof could produce something magnificent, something that would last. And it has lasted. 23 centuries later, we're still reading it, still teaching it, still being shaped by it, still working within frameworks it established. That's not just historical importance, that's living influence. The Elements remains active in how we think, how we teach, how we organize knowledge. It's not a relic we preserve out of piety, it's a foundation we continue building on. Euclid created something that outlasted empires, survived dark ages, crossed cultures, and adapted to revolutions in human understanding. The Elements absorbed changes that would have destroyed lesser works. It bent without breaking. It remained relevant through transformation. That resilience comes from getting something fundamentally right. Not the specific axioms, which turned out to be revisable, not the particular theorems, which can be generalized, but the approach itself, the method, the commitment to clarity, system, and proof. Those values don't become obsolete. They're what make knowledge knowledge rather than opinion. They're what make thinking rigorous rather than sloppy. They're what make mathematics mathematics. Euclid didn't invent those values, but he embodied them so perfectly, demonstrated them so convincingly, that he became their exemplar. The elements showed what rational knowledge could be at its best. We're still trying to live up to that standard, still trying to be as clear in our definitions, as careful in our reasoning, as rigorous in our proofs, still trying to build knowledge that will last. That's Euclid's real legacy. Not a collection of geometric theorems, but an enduring demonstration of what human reason can achieve when it's organized, systematic, and uncompromising in its standards. The element stands as proof that such achievement is possible, and that proof endures because mathematics keeps proving it necessary. Every generation discovers Euclid anew, not as antiquarian curiosity, but as essential foundation. Students who think they're learning outdated material suddenly realize they're acquiring tools that still work, better than work, tools that reveal structure invisible without them. Consider what happens in a first geometry course today. A teenager encounters Euclid's approach, probably without knowing that's what it is. They learn to start with clear definitions, to state assumptions explicitly, to build arguments step by step, where each step follows necessarily from what came before. This feels artificial at first. Why all the formality? Why can't we just see that the conclusion is true? But gradually something shifts. The student begins recognizing the power of the method, how it forces clarity, how it exposes hidden assumptions, how it creates certainty rather than just plausibility. That moment of recognition happens millions of times every year. In classrooms across the world, young minds encounter Euclidean thinking and discover its strength. They don't always love it. Rigorous proof is hard, but they can't deny it works. And then they carry that training elsewhere. Into physics, where systematic reasoning about forces and motions follows Euclidean patterns. Into computer science, where algorithms demand exactly the logical precision Euclid exemplified. Into law, where careful argument from principles to conclusions mirrors geometric demonstration. Into philosophy, where clear definitions and valid inference remain the standard. The elements trained people to think this way long before these fields existed. It established the template. Other disciplines adapted the approach because it proved effective. Mathematics showed what was possible. Everyone else followed. But here's something strange. The more we extend Euclidean methods, the more we discover their limits. And those discoveries don't diminish Euclid, they honor him. Non-Euclidean geometry didn't destroy the elements. It revealed how deep Euclid's insights went. By changing one axiom, mathematicians created entirely new geometries. Consistent, rigorous, useful. The parallel postulate turned out to be independent. You could deny it and still build valid mathematics. This was shocking when Bolyai and Lobachevsky first demonstrated it in the 1820s. 2,000 years of assuming Euclidean geometry was the only geometry. Then suddenly there were others, equally legitimate, equally rigorous. Some saw this as refuting Euclid. They were wrong. It vindicated him. The elements had established standards so clear that mathematicians could recognize when they'd created something genuinely different. Euclid's axiomatic method was what made non-Euclidean geometry possible. His insistence on stating assumptions explicitly revealed which assumptions could be changed. You can't modify what you haven't clearly identified. Euclid identified everything. That transparency enabled revolution. Einstein would later use non-Euclidean geometry to describe space-time in general relativity. The universe, it turned out, isn't Euclidean at cosmic scales. Gravity curves space. Parallel lines can meet. The fifth postulate fails in the real world. Does this mean Euclid was wrong? Not remotely. It means he was asking the right questions. He isolated the assumptions needed for flat space geometry. He built the system so carefully that later mathematicians could see exactly where to deviate. His clarity made their breakthroughs possible. This pattern repeats throughout modern mathematics. Euclidean geometry remains foundational even as we build beyond it. You learn Euclid first because his approach teaches how mathematics works. Then you extend, generalize, abstract. But the core method stays Euclidean. Clear definitions, explicit axioms, rigorous proof. David Hilbert's axiomatization of geometry in 1899 was essentially a refinement of Euclid. Hilbert filled gaps, made assumptions more precise, brought the elements up to modern standards of rigor. But he was working within the tradition Euclid established, improving, not replacing. That's the sign of a truly foundational work. It doesn't become obsolete when we advance beyond it. It becomes the launching pad, the reference point, the thing we build from. Mathematicians still cite Euclid, not ceremonially, practically. When introducing axiomatic systems, you explain what you're doing by reference to the elements. When teaching proof techniques, you use Euclidean propositions as examples. When discussing mathematical methodology, you invoke Euclid as the standard. 23 centuries. Still relevant, still useful, still teaching. How many other books can claim this? The Bible and a handful of philosophical texts, perhaps. Works that address eternal human questions. But the Elements does something different. It provides a method that keeps working regardless of what we discover about reality. It's not tied to a particular worldview. It's pure technique. And that technique scaled in ways Euclid couldn't have imagined. He was studying points, lines, circles, triangles, concrete geometric objects. But his approach works for abstract spaces with infinite dimensions, for algebraic structures, for logical systems, for anything that can be organized axiomatically. Modern mathematics is vast. Specialized fields multiply faster than anyone can track them. But they're all recognizably mathematical because they follow principles the Elements established. State your terms clearly. Identify your assumptions. Prove your claims rigorously. That's Euclidean, even when the content is utterly foreign to anything Euclid studied. The Elements gave mathematics its character, its personality, its standards and values. Other ancient mathematical traditions existed. Babylonian, Egyptian, Chinese, Indian, all produced sophisticated results, but they didn't organize knowledge the way Euclid did. They didn't make proof the central requirement. That became mathematics' defining feature. Not calculation, not problem solving. Proof, demonstrated certainty. Knowledge you could stake everything on because it was logically necessary. Euclid made that the standard. Mathematics became the science of what must be true, not just what happens to be true. Of necessary relationships rather than contingent facts. That's an extraordinary shift, and it came from one book's uncompromising commitment to demonstration. The influence extends beyond professional mathematics. Euclidean thinking shaped how educated people approach problems. The expectation that claims should be justified, that arguments should be coherent, that conclusions should follow from premises. These aren't natural human tendencies. We're quite comfortable with contradiction and weak reasoning most of the time. But Euclidean standards created pressure toward rigor. They established what good thinking looks like. They made logical sloppiness recognizable as sloppiness rather than just normal discourse. The Elements raised expectations. This matters in ways we rarely acknowledge. Democratic deliberation assumes participants can recognize valid arguments. Scientific progress depends on researchers accepting demonstrated results, even when they're inconvenient. Legal systems require distinguishing solid reasoning from sophistry. All of this needs populations trained to value logical rigor. Where does that training come from? Partly from mathematics education, from encountering Euclidean standards during formative years, from learning that some arguments are simply better than others. That validity isn't subjective. That reason can compel agreement. Not everyone learns this lesson, not everyone accepts it, but the standard exists. We can point to it. We can say, this is what good reasoning looks like, and show them Euclid. The Elements provides an existence proof for rational knowledge. It demonstrates that clarity and rigor are achievable. That demonstration matters more now than ever. We live in an age of information, abundance, and epistemic chaos. Claims multiply faster than verification. Certainty seems impossible. Truth appears subjective. Against this confusion, mathematics stands firm. It still produces knowledge you can rely on, still builds understanding that actually accumulates, still achieves consensus through demonstration rather than power. The Euclidean model still works, and the Elements still teaches it, still shows students that knowledge can be organized systematically, that difficult questions can be answered definitively, that human reason can achieve something permanent. This isn't nostalgia. It's not reverence for antiquity. It's recognition that Euclid solved a problem we still face. How do you create knowledge that lasts? How do you build understanding that survives the collapse of empires and the transformation of cultures? How do you make something that will still matter in 23 centuries? The answer is in the Elements. You define your terms precisely. You state your assumptions explicitly. You prove everything rigorously. You organize systematically. You aim for clarity above all else. You build from foundations upward. You accept nothing without demonstration. Do this and you create something that can't easily be destroyed, because it's not held together by authority or tradition or cultural context. It's held together by logic, and logic doesn't depend on circumstances. It just is. That's why the Elements survived. Not luck, not accident, not historical peculiarity, but because it was built to last. Euclid created a structure so sound, so well-founded, so rigorously constructed that it could endure anything history threw at it. Fire, conquest, cultural transformation, scientific revolution. None of it mattered. The arguments still worked. The proof still held. The system still stood. We can't all create works that last millennia. Most of what we build is temporary by nature. But we can aspire to Euclidean standards in whatever we do. We can aim for the clarity that makes ideas transmissible across cultures, the rigor that makes arguments survive critique, the systematic organization that makes knowledge cumulative. These are Euclid's gifts to us, not specific theorems about triangles, not particular facts about circles, but an example of what human reason can achieve when it's deployed with discipline and care. A demonstration that knowledge can be permanent, that understanding can accumulate, that we can build things that outlast us. The Element stands as proof, not just mathematical proof, but existential proof. Proof that creating something truly lasting is possible if you're willing to meet the standards it requires. 23 centuries later, we're still learning that lesson, still being shaped by an example set in ancient Alexandria, still working in the long shadow of Euclid, still trying to match the clarity, rigor, and systematic thinking that made one book immortal. The Elements endures because it earned endurance. It built itself to last. Every definition careful, every proof rigorous, every proposition necessary. Nothing wasted, nothing arbitrary. Just pure, clean, logical necessity from beginning to end. That's what survives. That's what matters. That's what we remember when everything else is forgotten. Not the man, not the circumstances, not the culture or the era. Just the work. Just the achievement. Just the thing itself. Standing alone, speaking for itself, proving itself across the centuries. Euclid showed us what that looks like. The Elements is still showing us. And that lesson, like the book itself, shows no sign of growing old. What would we find if we could somehow visit Alexandria in 300 BC and watch Euclid work? Probably something disappointing. A middle-aged man in a modest house, surrounded by scrolls, working methodically through proofs that already existed in rougher forms. Nothing dramatic, no lightning bolt of inspiration. No sudden breakthrough that changed everything. Just patience, just discipline, just the slow, careful work of organization. He wasn't discovering most of this mathematics. He was arranging it, taking scattered results and weaving them into systematic order, finding the right starting points, determining the logical sequence, making everything explicit that earlier mathematicians had left implicit. It sounds mundane, it was revolutionary, because what Euclid understood, what perhaps only he fully grasped, was that organization is itself a form of creation, that taking existing knowledge and structuring it properly produces something genuinely soi. Not new theorems necessarily, but new understanding, new clarity, new power. The elements didn't just collect geometric results, it showed how they all fit together, how they formed a system, how they could be derived from a handful of basic principles through pure reason. That systematic unity was Euclid's contribution, and it changed everything. We know almost nothing about him as a person. No portrait survives, no letters, no diary entries revealing his thoughts or personality. Just the work, just the book, just 13 scrolls of systematic geometry that would outlive empires. Maybe that's fitting. Maybe it's what he would have wanted. The mathematics speaks, the proofs stand, the system endures. What else matters? His name became synonymous with his subject. Euclidean geometry. Not Greek geometry or ancient geometry or classical geometry, Euclidean, as if he owned it, as if he'd created it from nothing. He hadn't, but he'd done something almost as impressive. He'd taken a field and made it definitive, made it complete, made it his through the sheer force of systematic organization. 2,000 years, that's how long the elements remained the geometry textbook. Not one option among many. The option, the standard, the thing you learned if you wanted to understand geometry properly. Think about what that means. A book written in Alexandria around 300 BC was still teaching geometry in Europe in 1900 AD. Students in medieval monasteries learned from it. Scholars in Islamic courts studied it. Renaissance artists used it. Enlightenment scientists built on it. Victorian schoolchildren memorized it. The same book, the same proofs, the same logical structure, preserved, transmitted, translated, copied, but fundamentally unchanged across centuries of human history. Nothing else matches that longevity. The Bible was constantly reinterpreted, scientific texts were superseded, philosophical works were debated and revised, but the elements just kept teaching, keep proving, kept showing each new generation what mathematical reasoning looked like. Why? Because Euclid got it right. Not just mostly right, actually right. He identified the real foundations of geometry. He built the system so carefully that nothing needed changing. You could add to it, later mathematicians certainly did, but you couldn't improve the core. It was already as good as it could be. That's an extraordinary achievement. To do something once definitively, so well that nobody needs to do it again. To solve problems that stay solved. To answer questions that don't require re-answering. The parallel postulate controversy actually proves this. For 2 millennia, mathematicians suspected the fifth postulate wasn't really necessary. They tried proving it from the other axioms. Countless attempts, all failed. Because Euclid was right, it was independent. You needed it. The system wouldn't work without it. When non-Euclidean geometries finally emerged in the 19th century, they didn't refute Euclid. They vindicated him. They showed he'd identified exactly the right axioms. Change one, and you got different geometry. But the method remained Euclidean. Clear assumptions, rigorous proofs, systematic organization. Euclid had established how geometry should be done. Later mathematicians followed his template, even when contradicting his conclusions. That's ultimate influence. Einstein's general relativity uses non-Euclidean geometry to describe spacetime. The universe at cosmic scales doesn't follow Euclid's rules. Does this make the elements obsolete? Not remotely. It remains the geometry of everyday experience, of human scale, of the world we directly inhabit and build within. Your house stands according to Euclidean principles. Your maps use Euclidean distance. Your computer screen displays Euclidean graphics. The geometry Euclid systematized 23 centuries ago is still the geometry we live in. But beyond practical application, there's something deeper. The elements demonstrated what systematic knowledge looks like. It showed that you could start with simple foundations and build vast understanding through pure reason. It proved that rigorous organization could make complex subjects comprehensible. That lesson extended far beyond geometry. Scientists adopted the axiomatic method. Philosophers tried to achieve geometric certainty in ethics. Mathematicians applied Euclidean standards to new fields. The approach became the template for serious knowledge across disciplines. Not everyone could match Euclid's success. Most subjects don't allow complete axiomatization. Human behavior is messier than triangles. Historical events can't be proven like theorems. But the aspiration toward Euclidean clarity shaped intellectual culture for centuries. We still expect arguments to be logical. We still demand that claims be justified. We still value systematic thinking over chaotic intuition. These expectations have Euclidean roots. The elements showed what rigorous knowledge could be. We've been trying to meet that standard ever since. And mathematics itself, modern mathematics, vastly beyond anything Euclid imagined, still carries his DNA. The insistence on clear definitions, the requirement for explicit axioms, the demand for rigorous proof. These are Euclidean inheritances. They define what mathematics is. You can study abstract algebra or topology or category theory, fields that didn't exist in Euclid's time, fields dealing with objects he never conceived of. But you're still doing Euclidean mathematics in spirit, starting with foundations, building systematically, proving rigorously. The content has changed, the method remains. That's the real achievement. Not creating geometry. Geometry existed before Euclid, but showing how mathematics should work, establishing the standards, setting the bar, creating an example so perfect that it became the permanent model. The Elements is still active in the world, still teaching in classrooms, still shaping how students learn to think, still providing the foundation on which mathematical education builds. Not as historical curiosity, but as living knowledge, as something that still works, still matters, still teaches lessons we need. Walk into a high school geometry class, anywhere on Earth. The students are learning Euclidean geometry. Maybe they don't know that's what it's called. Maybe they've never heard the name Euclid. Doesn't matter. They're encountering his methods, his standards, his approach to systematic knowledge. That's immortality. Not the immortality of fame, though Euclid certainly has that, but the immortality of influence, of continuing to shape minds centuries after your death, of remaining present in how people think. We don't know what Euclid looked like. We don't know his personality. We don't know his private hopes or fears. We know almost nothing about him as a human being. But we know what matters. We know what he built. We know that it lasted. We know that 23 centuries after he put stylus to papyrus in Alexandria, we're still using his work. Still learning from it, still being shaped by standards he established. The Element stands as proof that certain kinds of achievement transcend time. That if you build something sound enough, clear enough, rigorous enough, it can outlast empires and survive revolutions. That human reason, properly organized and carefully applied, can create knowledge that's genuinely permanent. Euclid showed us this was possible. The Elements continues showing us. Every student who works through a geometric proof is receiving that demonstration. Learning that systematic thinking produces lasting understanding. Discovering that clarity and rigor aren't just stylistic choices, but paths to truth. The man disappeared into history. The work remained. And perhaps that's the most Euclidean outcome possible. What endures is what deserves to endure, Not reputation, not personal details, not biography or circumstance, just the thing itself, the achievement, the proof. Euclid of Alexandria lived sometime around 300 BC. He probably taught at the museum. He possibly studied in Athens. He certainly wrote the Elements. Beyond that, we know almost nothing, and yet we know everything that matters. We know he created something that would outlast pyramids. We know he established standards that would shape human thought for millennia. We know he built a foundation so solid that everything erected on it since has stood firm. That's enough. More than enough? The element speaks for itself. The proofs demonstrate their own validity. The system proves its own worth through 23 centuries of continuous use. Nothing else needs saying. The work says it all, which is perhaps exactly how Euclid would have wanted it. Let the mathematics speak. Let the logic stand. Let the system prove itself. It has, it does, it will.